All right, continuing with section 5.5, we did 5.1, and now we're doing 5.5.1, and now we're doing 5.5.2, which is decay. But instead of using a different equation, we're going to use that same equation and recognize, just like we saw when the population growth was a decrease, the rate can be negative, and that is essentially decay. So we'll use that same formula, so we don't have to memorize more than one formula. And 23 through 26, your homework is 23 through 26. So we're going to do 24 and 26 together as a class, and then that will leave 23 and 25 for you to do on your own. So for number 24, we're going to use that same formula. I'm going to write it down here. And this time we're given a new concept called half-life. So half-life means how much time does it take to get half of the initial value. So the initial value is half of it's the amount of time, the t, when your amount is half of the initial value. So we're told that our half-life is equal to 1,600 years. So that means at n of 1,600, we have half of the initial value. And we also know from this formula, that n of 1,600 equals the initial value times e to the rt. But t, we just said, is 1,600. Whoops, sorry. So now I can use those two. Actually, you know what? I'm going to write it as two separate equations, just so you can see the difference. So the initial value, n of 1,600, is initial value times e to the r. T is 1,600. Now these two are equal. So I can set this guy equal to this guy to find out what the rate is. So I'm using the half-life to find the rate rather than being given the rate. So half of the initial value equals the initial value times e to the r t. Then we can divide both sides by and not. Our initial values go away. So even without without knowing what the initial value is, we can use the half-life to find the rate. So then we get half equals e to the rt. I'm going to write it as 1,600 r, so I have my variable second. And then I can take the natural log of both sides to get the variable out of the exponent, because I can't really get to that r without the natural log. And then when I take the natural log of e, those cancel and my exponent comes down, and I get the natural log of 1/2 equals 1,600 r. And then dividing both sides by 1,600, I get that the rate is the natural log of 1/2 divided by 1,600. I'm going to leave that rate like that for now, because now we're going to use that rate in our problem to answer. I'm going to use a different color for this part. How long will it take 5 grams to reduce to 2 grams? So we have our initial value is 5 grams. We want to find out when will we have 2 grams. We just found out our rate is natural log of 1/2 divided by 1,600. And I just want to solve for t. So I'm going to plug these three things into here and then find t. So our n of t is 2. The initial amount is 5. R is the natural log of 1/2 divided by 1,600. And we have to find t. So to solve for t, I have to solve for the variable is an exponent. So first step is to get that exponential section alone. So to isolate that, I'm going to divide both sides by 5. I get 2/5 equals e to the natural log of 1/2 over 1600 t. So to solve for t, I need to take the natural log of both sides to get the exponent out, to bring it down. So I'll take the natural log of both sides. Whoops, I didn't mean to do that in red. That should be natural log of both sides and when I take a natural log on the right, my natural log and my e will cancel. My exponent comes down. And I get natural log of 2/5 equals natural log of 1/2 divided by 1600 times t. So to isolate t, I want to multiply by the reciprocal of this fraction here to get t by itself. So I'm going to multiply both sides by 1600 over the natural log of 1/2. So that gives me that t equals 1600 natural log of 2/5 divided by natural log of 1/2. And now I'm going to get my calculator to get that value to estimate. To answer that question, how long will it take? I got to find out. My answer is going to be in years because my half-life was given in years. So now let's get my calculator out. I have 1600 times the natural log of 2/5 divided by natural log of 1/2. So that is approximately 2,115 years. So to answer that question, how long will it take 5 grams to reduce to 2 grams? 2,015 years. Sounds like a lot, but if I think back to my half-life was 1,600 years, this is a little bit more than half. So the answer does make sense. All right, going on to number 26. For 26, we have a drug has a half-life of 12 hours. And the initial dose is 5. We want to find out how much will be in there after 16 hours. So again, we need to use the half-life to get the rate because we have the time, we have the initial. We need to find the amount in the patient's body after 16 hours. We have the initial, we have E, and we have the time is 12, but we don't have R. So, I probably should have, hang on a second. Time is 16, sorry. There. So to find R, we're going to use the half-life. So remember, half-life means half the initial amount happens at N of 12 hours. And N of 12 equals the initial amount times E to the RT. Here T is 12 because we're told the half-life is 12. So that's a 12. And then I can set this guy equal to this guy because my N of 12 are equal. So half of the initial amount equals the initial amount times E to the RT. I can divide both sides by the initial amount, so I'm left with half equals E to the RT, and then I can take the natural log of both sides to get the when I take the natural log on the right, the e natural log e cancels, and my exponent comes down. So to get r by itself, I get natural log of 1/2 divided by 12. Keep that as a ugly fraction for now because I want to use it, and when I over here to find out n of 16. So n of 16 equals the initial amount, which is 5 milligrams, right? Our n naught equals 5. T equals 16. And our r is down here. So that's n naught times e to the r t, which is 16. So this one, I just need to calculate the stuff on the right-hand side. So I'm going to get my calculator for that. All right, so we have 5 times e to the power of natural log of 1/2 times 16 divided by 12. And I get, this is going to be an approximate now, 1.984 milligrams. After 16 hours. Okay, so that means that after 16 hours, the patient's body will have about 1.984 milligrams of whatever drug this is. All right, so, and that is exponential decay.